All right. Um, Thank you. Um, I'm very happy to share my work today. So actually, I'm also a big fan of soda, and basically, I watch almost every soda meeting. So today I'll be talking about a new work we did recently. It's about a Python framework for metabolomics data processing. So I changed the title a little bit to focus on the accuracy today. Mostly because we in metabolomics data processing, everyone knows we use automated software tools to handle this large volume of mass spec data. However, the accuracy is always a problem. So a lot of manual works are needed to correct the data for publication purposes. So that's why I made this work, and I want to share some details with you. So a little bit background for metabolomics. So I think metabolomics is very important. Also, it's different from um, like genomics or proteomics. Um, the very interesting part here is that by studying metabolites, we can not only look at the endogenous metabolites, but we can also look at those extraneous chemical compounds like food or microbe compounds or drugs and others. So if we look at the human serum metabolome, about one third of those detected chemicals, they are from the outside of our body. It's not produced by ourselves. So studying metabolism is important, and it has a lot of applications. And the basic for those application will be data processing. So data processing in metabolomics, no matter what platform you use, it can be abstracted like this graph, right? We have the raw data, which is produced by mass spec, and in the end, we want to have all the chemicals, their chemical structures, and their quantities for biological interpretation. The part in the middle, I use a worker here. It looks like a black box. And this part is called data processing. It convert the raw data or extract those chemical information from raw data. And conventionally, people do it manually, right? Like back in 20 years ago, we have LCMS platform. It's already mature technology, but by that time, most people they do manual picking. So you have five peaks, and people label those peaks and do the peak area calculation or peak height calculation, and then people do quantification. But right now, if we are talking about metabolomics, then it cannot be done manually, right? Because we have thousands of metabolites, we have thousands of samples. And the most important thing is that a single molecule can generate a lot of mass spec, a lot of charged ions, right? So in MS1 scan, we have this different adducts with the different isotope signals. And for MS2, different adducts, they have the different MS2. And in the end, they will have the different insource fragments. So insource fragments is also a very hot topic today. So we will have another friend to talk about insource fragment later, I believe. So insource fragment is a problem in metabolomics data processing. If we recognize the insource fragment as a real metabolite, that's a big problem, right? We have a false positive annotation here. So with this problem, so we have to use an automatic approach to systematically annotate those mass spec signals. So that relies on a software tool for data processing. So as here you can see, because a single molecule can have over than 10 different ion species easily, so it will be very difficult to recognize all those signals one by one. Um, so the conclusion here is the worker must be a software. And during the past 20 years, I believe there are a lot of great development on software tools. XMS, MZmine, now MZmine 3 has a very good functionalities, and MS Style also is now MS Style 5.0. And we have Maven. Also, we have some vendor software. Of course, this software is not free, like Compound Discover from Thermal. And also there are a lot of other software. They don't have a user interface. They are a Python package like a Sari. We have the past, I think we invited Sari author to introduce that software too. That is also a Python package to process metabolomics data. So with all those software, and most people they don't know which software to choose, right? And today I will be answer those questions. Like when we choose a software, what should we consider? And is this software have those software be carefully benchmarked? So that's also a question we want to answer today. So in this case, I will just show this graph to show the entire workflow for metabolomics data processing, right? So those are functionalities of MassCube. So I won't go through all those functionalities here, but the idea is to show you when we have the raw data, here's what we usually do. Like we import the data as MZML or MZXML format, and we do feature detection, feature evaluation, which means here we want to only focus on the real peak. People say real peak, which means it's not background noise or any other contaminants. And we do feature grouping to recognize isotope, adducts, and insult fragments. And we do alignment, and to basically alignment means we find the same chemical compound across different samples, right? We want to align the features. And then we do annotation, statistical analysis, visualization, and export. So a lot of developments in metabolomics only focus on one or a couple of steps in this workflow. But anyway, to combine those informatics tools, we can process the raw data and get all the chemicals and their quantities. So today I'll be introducing four important developments in MassCube. So, and we will also talk about other software tools, like how this problem was approached previously and what we can do better in the future. So the first challenge is the feature detection. Also, feature detection is the main focus of MassCube today. So the question started from my PhD work. So during my PhD, I noticed that I used MassStyle by that time. So when I look at my data, I think just like other software, so peak picking is never perfect, right? So sometimes you have the bad peak integration. You have a part of peak, they were not integrated by the software, and you probably if it's an experienced chemist, we believe okay, this should be just one feature, but the peak area was not recognized. So, but that time I only reported this problem. But if we think about this problem a little bit hard, we will realize like the problem is even more complicated because when we detect a peak, there are at least three peak parameters that can make the problem difficult. So first reason is the signal to noise ratio. If there's more noise, then it's more challenging for the software to recognize. Also, it can introduce false positive, which means a noise signal fluctuation might be recognized as a real peak. All right, and intensity ratio happen to isomers. So on the right side, you can see if we compare these two plots, if the intensity ratio change from 3 to 1 to 5 to 1, then this small peak on the side is harder to be recognized. This is also difficult, especially when software using smoothing function, right? When smoothing happen, this signal, this local minimum is even smaller. So then the peak is harder to recognize. And peak resolution happened when we have the isomer peaks. On the first two plots, you can see if the resolution changed from 1.5 to 1, then it's harder to recognize. But because there's no noise, I still think this is an easy problem. Like all the software, they should be okay for this one. But if we have the high noise level, low resolution, and clear intensity difference, then it could be hard. I mean, even analytical chemists, they probably have a different opinion on those questions. So untargeted feature detection could be very difficult because in the real data, there are noise, there are like empty scans, there are gaps in the middle. So our question is how is first, what current leading software, how can those good software approach this problem, and what's their performance, and what can we improve? So the rationale to metabolomics is, from my understanding, the feature detection should be in this way, like one type of ion should be reported to one feature. So if it's a background ion, because when we see one feature, feature is characterized by by a unique pair of MZ value and retention time. So then an ion should be, so this MZ and retention time should just be one chemical. So then we can define false positive, which means a single ion is reported as multiple features, and false negative is a unique ion is not reported. So in this case, we will be able to define what is a false positive and what is false negative. So then we can do some benchmarking. So in this case, if it's the isotope ion, it's ion pair, then it should be resolved and reported as a two features. If the software only report one or report three, then it's not correct. So if the background ion, so if it's a background ion, it should be reported as single large feature that spans from the start and the end of the chromatogram. So, the conventional approach is called readout change strategy. So this is the picking algorithm in MS style. So it checks the derivatives of the peak, but this problem is this approach is limited by three problems. First one is it requires sufficient scan numbers, and right now we use photography, and in many cases we want to make the gradient shorter, and as a result, the peak width is thinner. So many peaks, they probably only have 5 or even lower scan number. Second, it's sensitive to signal fluctuation because it's checked the derivatives. And then as a result, it will be sensitive to noise. If you optimize the parameter to be robust to noise, then you probably smooth the signal too hard. And the third problem is computational cost is also a concern, especially we want to deal with a large scale metabolomics data set. So in MassCube, in brief, we have the signal clustering plus edge detection algorithm. So the idea is actually the idea is inspired by XCMS picking algorithm. So it's the first try to group the signal with that showed up in consecutive MS1 scans. Okay. And then we do edge detection to segment this feature. And also there is a noise recognition algorithm. So if it's a background noise, then don't cut it anymore. Just I found many software did report a background noise to maybe 20 different features. So as a benefit here, so conventional approach, it requires sufficient scan numbers, but MassCube, because it do signal clustering, it doesn't require any scan number here. If it's a single scan but have a good MS2 spectra, I think it's still valid to export to report those signals. And actually, in the real practice, we found some metabolites they just have a peak like this. And the second is sensitive signal to noise, but here we just don't check the readout change, but instead we check the local minimum, and we check the difference of the local minimum to the left peak and right peak. So so the algorithm is more robust to the signal fluctuation, and also the computational cost is lower, and we use array programming in Python, so it's efficient. So systematic mass spec data processing benchmarking is an important problem. So a challenge is most comparison did before basically they compare feature number, or they compare consistency in data processing. But the question is more feature doesn't mean more consistent, also doesn't mean better, because people just get wrong. So the solution is that we want to have a synthetic mass spec data. We want to have a ground truth for benchmarking. So the solution here is that we generated artificial mass spec data. We inject the mass spec signal to MS1 scans, and we get a LCMS data. So the data is MZmine format, so it can be taken by any software for later processing. So then the data can be taken by any software. So So in the end, we have a large number of signals that were injected to the data, and we use this data for benchmarking. So here we can see so there are two different type of signals. One is called double peak, which means, as I said, this is a shoulder peak, and in principle, it should be resolved and reported as two features in the end. And on the other side is the single peak. So there are some noise levels, so we don't want to report more than one peak in this case. And in this development, we can see MassCube achieves the highest accuracy, like average accuracy in this two testing scenario. For single peak accuracy, we can see XCMS is very robust. It's very robust to noise, but in the end, it has the less resolving power for those isomer peaks. So, and we also benchmark using experimental mass spec data. So the data set is a total of over 200 of EIC plots, local EIC plots. And we manually label how many peaks should be reported in this retention time range. For example, in this case, it should be 2. And on the example lower, this plot shows this feature was only resolved by MassCube, but not resolved by other 3 software. And in real testing cases, so MassCube achieves significantly higher accuracy compared to other software tools. Also important, so here we compare the speed using 4 different metabolomics data sets with a different number of samples. So basically, the efficiency of MZmine is also good. So here we can see MassCube is much faster than MZmine, than MS-style and XMS, but with a similar speed to MZmine 3. So we tested we challenged MassCube to process Orbitrap astral data. So it's over 600 data, and because the new Orbitrap astral data was created, I mean the MS2 acquisition is much improved. So then the data size was also improved. So with this 8-fold increase the data size, we achieved like the end-to-end processing on a personal laptop in 64 minutes with a parallel processing. So the second challenge, I'll just speed up a little bit. It's called feature grouping. So I'll just also set up a stage for Yasin later. So feature grouping conventional tools mainly focuses on isotopes and adducts. And as I said, insult fragment is also an important challenge that should be considered. So in MassCube, we consider 2 criteria. So first one is the insult fragment should be present in the MS2 spectra of the parent ion. So then we have a good evidence to say, okay, this is very likely to be a fragment. And the second, we check their elution profile. So they should have the identical peak shape. So we use the peak correlation to recognize insult fragment. So the plot here we can see here are 2 internal standards, and we can recognize this insult fragment respectively. And also an interesting problem is this 2 insult fragment has the same MZ value. So it also shows our software can resolve these 2 peaks. So the third challenge is called retention time correction, and even this is not the main focus of MassCube, but I just want to highlight a retention time error can cause a lot of problem, especially in quantification, because on the left side you can see before correction, if there are 2 batches, it's a batch 1 data, batch 2 data, if there's no retention time correction, alignment may you might align features to a different features, and we call it cross alignment. And if a feature was not aligned to anything, so this feature should be aligned to here, right? But it's not aligned to nothing. So it's called a misalignment. So then you have a lot of gaps in your data. So that's why we select the feature and we use a feature with a unique MZ value as retention time anchors for correction. And I think other software, they also have the retention time correction function, and hopefully in the future we can have another work to benchmark the performance of this retention time correction algorithm. So, but here's a functionality that was provided in MassCube for accurate quantification. So finally, it's called feature annotation. So in MassCube, we try to expand the conventional identity search to analog search. So this is what we did in the conventional approach. We match all the fragment ions to the database, also including precursor ion. Exactly. So which means if the compound is not in the database, we have zero information about this feature. But but later we have but right now we like last year like in 2023 we have a paper to summarize like different type of searching algorithm. So the algorithm actually was inspired by molecular networking, so by GMPS. So in GMPS, we GMPS tries to consider like the relationship between different MS tools within a study, and here we use this idea to do the annotation by matching a compound in by matching MS2 in the data to all the spectrum in the database. So the calculation will be a problem because if we do, for example, hybrid search, then we remove the restriction of precursor ion, then the calculation speed will be a problem. So in 2023, in FinLab, there's a work called flash entropy search that can achieve this calculation in a very fast speed. Also, it's a Python package. So then this package has been implemented in MassCube for metabolite annotation. So with the fuzzy search, here we can see if we only do identity search, we can only annotate this blue dots in the data, right? So this is the mouse brain data set we use for demonstration. But with the fuzzy search, we will be able to annotate a lot of other compound. Especially here, we can see this is the lipidomics data. So we hypothesize those metabolites, those features on the top, this will be 2M plus H or other different adducts, but they are not in the database. But in this case, they can be recognized. But the more important or more interesting thing is that we can find some like chemically modified compound from the known compound. So then we go back and look at this graph. So MassCube provide we call it in the title we call it end-to-end data processing, which means from the raw data, if you use MassCube, you can get all the chemicals and their quantities. But in the middle, we care about all those details, and we try to achieve the human expert level accuracy in this automated data processing. So how to use MassCube? It doesn't have a user interface, so it scared a lot of our users in our beta testing. But actually, to use MassCube is very simple. So we have, I basically I prepare command line application. So first one, all you need to do is to create a folder and prepare three stuff. You have the data and the ML in your folder. You have the parameter. If you don't provide a parameter file, MassCube will just use a default. And you need a sample table. So, and then in the project folder, we open terminal and we run untargeted metabolomics. Then you're done. So then we'll get a lot of output like align feature table. You have the visualization result. You have the single file peak picking result, signal normalization result, and many others. MSP for MS2 spectra. If you want to further annotate those spectra using GMPS, you can just take this MS2 and import to GMPS. So in the feature table, we have some new information compared to the conventional data report. We have the group ID. If multiple features, they have the same group ID, then they belong to the same feature group. All right, they are very likely to be generated by a same neutral molecule. In the adducts, we have the detailed annotation about their forms, and we have the column to see if there is an isotope or in-source fragment, and we have the peak evaluation criteria here. And for MS2, we also have those information. So in the folder, there are all the output you will have, but some interesting plots here will be you can get a base peak chromatogram to check the data quality. You can get a mirror plot for spectral matching. You can get this plot to check the signal normalization result for signal drift correction, and this U map to just to overview the difference between your sample groups. So here's the project website, and thank you everyone to be here. And I'll just be very excited to share my work with you. And if you have any questions, feel free to email me, and also feel free to leave comments in our GitHub issues if you have any technical problem when you are running MassCube. Thank you.
Yasin, who is a postdoc at UCSD, and his title today is The Remaining Size of the Dark Metabolome. Take it away.
Thank you. Give me a second and I will share my screen. Okay, I hope you can see.
Yes.
The first slide, perfect. Okay, yeah, so first off, I want to thank Soda for inviting me to give the talk here. As you can see from the title, I'm going to talk about the remaining size of the dark metabolome, which I believe is a very important question with a lot of impact on how we perceive our own data sets, as well as, I would say, the whole field of metabolomics. Depending on how you answer this question, you will probably see many workflows in a very different light. This is a question that has been discussed already for a long time, and there has been also like recently again some, I would say, discussion about that. So there was this one paper that I've put here from Guerra et al. To which we recently responded with this other paper that I marked in red down here. And I want to talk here now a little bit about the workflow that we used to address some of the questions that were raised by this initial manuscript, because yeah, I think it's just some interesting workflow of the question itself is very interesting and impactful. So yes, what did they actually say? So you can see here a basic overview of their paper and their main claims. So for once, what they said is that we have basically very widespread interfragmentation in metabolomics data, exceeding 70% of all the signals that we see. And then they also make some conclusions on that. And yeah, most prominently, that the dark metabolome is basically largely made up of fragments ion generated during electrospray ionization, and therefore not unique metabolites that we could identify to learn anything new about metabolism. So what did they actually do to come to that conclusion? So what they did is that they used a very large library that they have internally available, which is MZmine. It consists of 930,000 standards, so a lot of standards. And what they did is that they basically looked at all the MS2 scans that they have generated for this library, which they recorded with 0 electron volts, which means that they would expect, as described in their paper, no fragmentation. So in other words, they expect that then they would go with 0 electron volts ahead to isolate the ions and then look at the signal. You should only see the precursor ion, but they saw that they saw more ions there, which they annotated then as in those fragments. So, and they said in general, they have about an average of 3 fragments per MS2 scan there. And from that data point, they extrapolated a lot of other conclusions that they made based on that. So for once, and I will now go through them one by one, and I agree, disagree, or partially agree with those data points. So I just put them here on the side so you can look at them already. But yeah, we will go through them one by one. And yeah, and if you want, I won't go through everything. So if you want to learn more about this, about our work on this, yeah, you can also go ahead and read the paper that we published there. And of course, I also didn't do that alone. There will be also acknowledgement slide in the end, but I definitely want to highlight already here Adriano Rutz, yeah, whom I worked with on this project. Yeah, quite a lot. So how did we address this question? So the first thing that we did is that we went ahead and also looked at, I hope you can see here on the top, and it's not hidden behind this bar. Yeah, we looked at an MS2 library that we had that's in the public domain. It was a while ago published by Brunks Corina et al. It's in Chem Archives at the moment. And what they did is that they looked at 30,000 different analytical standards on the QE IDX experiment. And yeah, we went ahead and basically downloaded all this raw data and then looked at this raw data. And what you can do then is you can look at each and every of these standards that they have injected, and you can check for each of the MS2 peaks that you have there, if any of these MS2 peaks also shows up on the MS1 level. And if it does, you can basically assume, or be assumed in this case, that this would be inverse fragments. So in this case, we would assume that we have 3 inverse fragments, because here that one, that's just a precursor mass, so that one we would not count. And this is how we went ahead to do the same kind of statistic that they did. So we basically counted how many inverse fragments do we now see for each individual standard that we have injected there. So here you can see the statistics that we have made based on that. So here for the M+H ion of all these different ion species, you can see that we have a median of 2 inverse fragments per M+H ion species, which is in the ballpark of what they have also seen. They reported 3 fragments per MS2. And then when we look at other fragments, yeah, we saw considerably less inverse fragmentation for those, with medians negative ion mode for the proton loss of 1, and for the sodium adduct, we saw a median of 0. However, overall, I would say we were in the same ballpark of what they have seen. So I would say, yeah, for that, I would at least say I partially agree with what they see there. But yeah, I will agree less with like some of the conclusions that they made there, and I will talk about why. So for once, what they concluded from that is that they have 3 MS1 inverse fragments per molecular ion, really on the MS1 level, which is a very different claim than seeing 3 fragments per MS2. There was some work there. Yeah, and the way we basically tried to tackle this question is that we looked again at these molecular standards that we had injected. We also have some data on a TOF instrument there. And what we could show there, that if we went ahead to annotate the different species that we saw there at the MS1 level, we could see that based on overlap with the MS2s, the same way I just showed you before, we can annotate only a fraction of this MS1 scan as inverse fragments. And much of the other signals that we see, we can either annotate as some adducts, so that could be M+H, M+sodium, or anything else, or as isotopes. Overall, we were really just able to annotate at about 24% of everything that we could see of all the signals on the MS1 level as inverse fragment following this strategy. And this is also in the ballpark of what other people have seen, and I will come to that. I will come back to that a bit later. Yeah, so overall, I would disagree with this particular statement. Then when it comes to the next one, which is that 70% of features also in biological samples are inverse fragments, we tried to address this question by looking really at the intensities of the inverse fragments that we are seeing here, because we can, of course, following the strategy that I have showed you here, look always at the intensities that we see here on the MS1 level for these different inverse fragments. And when you do that, you will get across all these different ion molecules that we had there in this data set, you will get this kind of distribution. So we have that here for 2 different basically arbitrary classes of molecules that we have defined. Here we have all molecules down here, and then we just basically put out as a separate distribution molecules that have 2 or more hydroxy groups. So those are often more prone to inverse fragmentation due to water losses. And you can see that, yeah, there's indeed some difference there. And yeah, what really is what is really striking about the result is how low the intensity of many of these inverse fragments really is. So if you would want to see something here below the 0.01 threshold, you would only be able to see anything below that line if the precursor ion that you have in your data set is at least 100-fold over the LOD, which is something that, if you know biological samples, is not really that often the case. And if we look at that in even more detail, so if we go by insource fragment rank, so here we would have the highest insource fragment for each individual molecule. We would have a little bit higher median for the molecules, these two hydroxy groups, as well as for the general set of all molecules. We would have a little bit of a high distribution. However, if we go to the second, we already drop. We see that we drop to lower values very fast. So in general, many of these insource fragments just have a very, very low relative abundance. And so, if you know your biological samples, then you will probably know that many of your molecules that you are detected in there are not 100-fold above your limit of detection. And as a result, in many cases, you will not expect to see many of these insource fragments that you see in these analytical standards, also in biological samples. Okay, then further to the last claim that the dark metabolome is largely an artifact. We also addressed it from a number of we also addressed it from some different points of view. For that, we used some NIST fecal reference material data set that we have collected in collaboration with Thermo. This was on the UHBOC astral data set, and as you can see here, the reason why we used that is that if we go on with the strategy that we talked about before by using the MS2 scans to annotate our insource fragments, it's really important that we have MS2s for as many ion species as possible. And in astral data set, as you can see here, each blue marker here signifies an MS2 scan. That's the closest we can currently get to that scenario. The way we then use that is that we first did feature detection on these different fecal reference material samples that we had collected. We then grouped them all by correlation, as well as if they were co-alluding, even if they were not correlating, we still grouped them together if they were overlapping with something that we saw on the MS2 level. The same logic that we also applied in the strategies that I showed you before. And by that, we basically grouped all the ion species that we saw into molecule groups. And that way, we could basically start getting an estimate of how many molecules we actually have in our data set. And then we could start annotating them. And the way we did that is that we said, if any of the ion species that we see in all of these molecular groups gets annotated, we just assume the whole molecule is annotated. This will obviously lead to a lot of false positive annotations, but we just really wanted to come up with an upper boundary of how much might be already known in this data set if we just are not strict at all by doing our annotations. And you can see here in the bottom plot how many of these molecules or putative molecules we have been able to annotate using this strategy, which was about 18%. And here in the upper histogram, you can see how much was left after that, and also broken out depending on whether we had sufficient or insufficient MSMS information to really do the annotation. And the way we defined that was that we said it's only sufficient MSMS information if you really have an MSMS scan for each individual of this ion species, and not just we have to have an MSMS scan, but it also needs to be non-chimeric, because if it's chimeric, it might just be that we're not able to annotate it just because the quality of the MSMS is bad. And yeah, as you can see, there's still a lot left to be annotated, even if we go with this conservative estimate. We also tried to shine light on that question from another angle than just this, to really drive the point home that there's much more to discover. And the way we did that is that we reused public data, because we did aggregate a lot of data in the public domain at this point. So we have way more than 1.5 million different samples at this point in the public domain that we can reuse to try answer this kind of questions. And also more than 1.5 billion different MSMS scans at this point. So yeah, we basically wanted to figure out how much is out there that might still be unknown. One way of going about that would be to try to really cluster all these different MSMS scans that we have out there. So basically, the way you would do that is you would take all these MSMS scans together and then find the ones that look similar to each other. And if scans are looking similar to each other, you could say, these are probably from the same molecule as an outer estimate. At the moment, this is not really something that's very easy, just computationally speaking, because 1.5 billion scans is quite a lot to process. So we just used some subset of these data sets to answer this question. And the data sets we chose was one human blood plasma and one fecal data set with 2,500 and about 1,500 samples respectively. And after clustering those within rarefaction curves, as you can see here, and if you don't know what a rarefaction curve is, it's basically just a way of taking more and more of your samples, clustering all the MS2 scans within these samples, and then seeing how the number of unique MS2 scans that you get grows as you add more and more samples to this. So this allows you to kind of see whether you get more chemistry that you didn't see in the samples that you already had by adding more samples. And what we did then is that we tried to just annotate the clusters that we got in this way. So for that, we used our GMPS library, which allowed us to also stratify everything by the year of publication in the library. So when you do this with the fecal and the plasma data set, and you only annotate with the library entries that you had in 2014, you can see that this would be the amount of annotation you would get in this way. And then once you add more and more different, once you add more and more years, you can really see how in every consecutive year, as we got more and more analytical standards into our library, we grew the number of annotations that we had there more and more. So you can see that it didn't really slow down the speed of discovery here. And every year we are discovering new molecules, even in this very well-known sample types, especially blood plasma, which I think is a very commonly analyzed data sample type. So overall, this is why we disagree with this statement that the dark metabolome is largely an artifact. We think that just looking at how much is discovered in every consecutive year, and also even looking at an individual data set like this NIST reference material, you can see that there's still a lot to be discovered. And this is why we really disagree with this particular statement. If you want to know more, I already mentioned before, you can just look at this paper. I also really recommend you the GitHub repositories that are associated with this paper, because much of the methods is actually in this GitHub repositories. Of course, there has been a lot of other work already done on interest fragmentation, which I think also really supports the point that we are making here. So here you have, for example, one study that I personally really like, which was published in Yasin some years ago, and they really showed that even if you just go for some different lipid species, if you jump from one instrument to another, or if you change their parameters, the amount of interest fragmentation you get really changes by a lot. So based on that, I think you can see that I'm sure you can reach very high numbers of interest fragmentation if you use the wrong settings for the kind of interpretation you want to make for your particular data. And other studies that, as you can see here on the other side, focused on estimating how much interest fragmentation there is in a particular sample, also like generally conclude that we have rather low numbers of interest fragmentation if you look at real biological samples and not at standard mixtures, where the percentages can indeed get very high because of the high concentrations of the analytical standards. And with that, I'm already at the end. I want to thank all the courses that we have in this paper. You can see a lot of people contributed there. Adriano Rutz, I already mentioned before, did also a lot of work on it. And and then also NIST for providing us the reference material, as well as the whole Doristin lab, and again also Soda for giving me the opportunity to present this research here. And thank you.
Thanks.
And open for questions.
It's great. Thanks a lot. Any questions?